Alright, so in this video I'm going to talk about predicting product for decomposition, combustion, and single replacement reactions. Alright, so first we're going to go over decomposition. And remember, decomposition reaction is when you have one reactant and it breaks down into many products. So the way that we're going to do these is you're only going to have to break them up into its individual elements. So break up reactant into its elements. So if you were to see something like this, you would then know that this was decomposition because there's only one reactant. There's only one reactant on this side of the reaction, so it can't be anything but decomposition. All right, and its elements are going to be sulfur and oxygen. So we're going to break it up into sulfur plus O2. Because oxygen is diatomic, it will always exist as O2. So then we have to balance the equation. So I need 3 of these, 2 here, and 2 here. And so that would be the answer. All right, and for the second example, let's say you come across something that looks like this. You would know that's decomposition because there's only one reactant, and it has to break down into its elements. So it's going to break down into H2 and Cl2. So for this, all you really have to know are which ones are diatomic. So when you're looking at the periodic table, it's always going to be nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So that's number 7 on the periodic table. It makes the shape of a number 7. And the 7th element is hydrogen. So all 7 of those that are written there, hydrogen, and then these 6 are always diatomic. And so they're always going to appear as 2 atoms, right? Diatomic. All right, so let's go on to the next type. And the next type is combustion. And so combustion reactions are always reacting with oxygen. So if oxygen, and it has to be O2, it can't be something else in the other reactant, is reacting with something, then you can use this. All right, so first we're going to look at hydrocarbons. And so remember that a hydrocarbon is something that has hydrogen and carbon and then sometimes oxygen. Okay? So let's say you run across something that looks like this. So you have C3H8 plus oxygen. You would know that this is combustion because it's reacting with oxygen. And since it's a hydrocarbon, it's always going to make CO2 plus H2O, because this right here is the definition of a hydrocarbon. It has carbon and hydrogen in it. And so this is always going to be your product for those, the CO2 and H2O, and then you can balance it. So we would need 3 of these, 4 hydrogen, or 4 waters to give you 8 hydrogen. And so that's 6 oxygen right here, and 4 oxygen, so that's 10. So we need 5 O2s. All right, and then our next example, it's also a hydrocarbon, and so it's also going to produce CO2 and H2O. So we're always going to assume complete combustion and that it's going to make CO2 instead of carbon monoxide. All right, so we have 4 carbons here, so I need 4 of those. And then I have 8 hydrogen right here, so I need 4 of these. So that's going to give me 8 oxygen here and 4 oxygen, so that's 12. I've got 2 oxygen right here, so I need 5 of these to give me 10 more, so that the oxygens balance out. All right, so another type of combustion is when a metal is burned. So let's say you see something like this. Now that obviously can't create carbon dioxide and water because there's no carbon or hydrogen here to make the carbon dioxide or the hydrogen for the water. So when we make this, we have to make a compound that exists. So the charge for magnesium is 2+, and the charge for oxygen is 2-. So the compound that would be produced between magnesium and oxygen is MgO. And then we could go back and balance the equation. So I need 2 oxygens and 2 magnesiums. All right, let's do one more like that. So we have aluminum and oxygen. Aluminum is 3+, and that comes right off the periodic table. Oxygen is 2-. So if we cross those down, we get Al2O3. So we need 2 here, 3 here, and 4 there. All right, so that's pretty much combustion. All right, there you go. Give you a second in case you missed anything. All right, so next we're going to go on to single replacement. Now, single replacement reactions are a little bit different. So we're going to learn how to use this activity series. All right, so this says reactivity series here, but it could also be called an activity series. And I've added something to yours. I've added this activity series as well. Okay, so they're separated from each other. So first we're going to talk about these right here. All right, so let's say that I put zinc into hydrochloric acid, into HCl. So first thing we have to do is we have to figure out if zinc will replace hydrogen. And zinc is right here, and hydrogen is right here. So yes, zinc is higher on the activity series. It's more reactive because it's higher on the top. So it can replace hydrogen. So that means that zinc is going to kick hydrogen out and take chlorine from the hydrogen. So hydrogen gets kicked out. And remember, hydrogen's diatomic. So we need H2. And then we have to find the compound that's formed between zinc and chlorine. And zinc is always +2. Chlorine is always -1. So it's going to form ZnCl2. So we need 2 of those. All right. Okay, so let's try another one. All right, so we have copper, and we put it in a solution of magnesium nitrate. And if we look at the activity series, copper is right here, and magnesium is all the way up here. So copper is not reactive enough to replace magnesium. So that means that this reaction will not happen. So when you do these single replacement reactions, you have to make sure that the single element must be more reactive than the element it's going to replace. All right, so let's do a couple more. Bring this thing down here. All right, so you see this, you would know it's single replacement because potassium is single right here. And so, is potassium reactive enough to replace magnesium? Potassium's all the way up here, magnesium is down here, so potassium can replace it. So that means magnesium gets kicked out, and potassium is +1, nitrate's -1, so you're going to end up with KNO3. So then we have to balance it. We have a 2 there and a 2 here. All right. One more. So here, this time, fluorine is by itself, and so we can't, fluorine isn't in this activity series right here, it's in this one. And so fluorine isn't going to replace potassium because we have no comparison for those two. And not only that, fluorine would have a -1 charge in a compound, while potassium would have a +1 charge in a compound. So they're never going to replace each other, they'd be attracted to each other. So since fluorine is more reactive than iodine, it'll replace it. So that means that iodine gets kicked out, and remember iodine is one of those diatomics, so it's I2. And then we have to look at the compound that would form between potassium and fluoride, and that would be KF. And so we would need 2 of those and 2 of those to balance this reaction. This really takes actually doing it. A lot of the time you can follow it fine, but it takes doing it to really feel comfortable with it. So I suggest you work as many problems as you can, and we'll keep working them in class.